We will begin by discussing the domain and range of a function. So first, whenever we're describing a function, the domain of the function is the set of all the input values. Now, probably most commonly, you would have heard of this in terms of the x values. Generally, x is used for inputs, y is used for outputs. The way you can keep that straight is if you've got x and y, input and output, x comes before y alphabetically, I comes before O alphabetically, input, output, it kind of alphabetically matches up. And the range of a function is the set of corresponding output values. And notice we use the word corresponding because the way a function works is a function takes an input value, and then based on the function relationship or the rule the function has, it sends that to a unique output value. Okay, so every input value gets sent to a unique output value. So in this picture, we've got this visual graph is just showing the input-output corresponding pairing for infinitely many points between -6 and 5. And the domain is a set of all x values that we see graphed here. So notice the least x value graph comes from, if you look at this last point that we see graphed here, if you go straight down, that corresponds to the x value -5. And then we see that the x values are graphed all the way. And notice it seems like it's approaching and getting closer and closer to +5. So for this graph, the domain is starting at -5 including it, and then going all the way to 5, but not completely reaching it because we've got this asymptote. So with these brackets, the square bracket means it can equal that value. The open bracket means approach, but not equal. So we can get as close as we can to 5, but not equal 5 exactly. And the range, the corresponding range values is, let's look, we've got y values. The highest y value corresponds to a y of +5, given by this point. And then as we look at the different y values, we see that the y values seem to be about here. And then as we get closer to the x value of 5, do we see the y values are going down, down, down forever and ever? That means the range, the y values at the smallest are going to -infinity. So when the output values, or on the y-axis, as you trace the graph, keep going down forever and ever without bound, that's the idea of going to -infinity. And the highest y value we see achieved is, at first we've got a high y value there, but then it dips. But then notice the highest y value is up at +5. And since that point is filled in, we definitely do equal 5. So that's just showing the domain and the range of this function. And specifically, the idea of interval notation is how we just describe the domain and range, because I said for the domain, it's all of these x values. For the range, it's all of these y values. And we use the closed brackets or the open brackets when appropriate. Now in that previous example, we were given a graph of a function, but we can represent a function from an equation, a graph, and a table. So we already saw how to look at the domain and range of a function given a graph. Now we're going to talk about how to find the domain of a function when given an equation. So for the next few examples, we are going to be given a function as an equation, and we'll need to be able to find the domain of the function and express this domain in interval notation. Now as you look at our first example, we see it's x² plus 3x minus 2. And we could characterize this example as f of x is a polynomial, because it's just powers of x, or constants of powers of x plus constants. So since f of x is a polynomial, we automatically know some important characteristics about the domain and range of polynomials. So since this is a polynomial, automatically we know the domain is all real numbers, but written in interval notation, it means it could take on any x value from negative infinity to positive infinity. And not that's just that it can take on those x values, it will take on all those x values. And the range, the y values, also will range from negative infinity to positive infinity. So remember, if you recognize that your function is a polynomial, then you automatically know the domain and range of a polynomial. So this will help maybe speed up some different problems. Now, our next function is a rational function, and we're going to learn more about these, specifically graphing rational functions, in a future section. But let's just talk about how to recognize that it is a rational function first, and then we'll discuss this particular function's domain and range. You know it's a rational function when it's a polynomial being divided by another polynomial, which we see we have here. Since we've got 2x being divided by x squared minus x minus 6. So we automatically know this is a rational function. And when we recognize a rational function, we need to think about where would this function have problems. Specifically, the idea of 2x doesn't have problems, it's a polynomial. Let's look at x squared minus 6 minus x minus 6. X squared minus x minus 6 does not have problems, it's a polynomial. And we just said polynomials have domain and range both positive from negative infinity to positive infinity. However, just because both polynomials never have quote-unquote trouble with their domain, they exist for all values of x, does not mean that one polynomial divided by another polynomial will not have problems. Specifically with this fraction, we know that fractions have trouble when the denominator equals 0. So the top can be whatever, but they have trouble when the denominator equals 0. So we do not want this to occur. So specifically, as we look at this rational function, we know that the top is not contributing any issue. It's just a polynomial. Top of a fraction is always fine. But if there is going to be an issue, it's going to come from the fact that we've got a denominator. So we've got to avoid wherever the denominator could equal 0, not because the polynomial has trouble there, but just because any fraction cannot have a denominator of 0. So as you're looking at a rational function, remember it's not just what makes up the function, it's the structure of the function, and what you're looking for here is fractions cannot have a denominator of 0. Denominator is a fancy word for the bottom of the fraction. So we know that this function will have issues, has domain issues, when the denominator, x squared minus x minus 6 equals 0. Now where specifically is that? We'll have to factor to determine that. I see this is a normal quadratic, so I'm going to hope it factors nicely. Let's see. X and x. Now let's look at the signs to know what we should expect in our factored form. Looking first at the sign of the constant, since this is negative, the only way that when you multiply things you would get a negative here is if they were opposite signs. So for instance, if one was positive and the other was negative, that means when you multiply the constants, the resulting constant term would be negative. And then looking at the next sign, since it's negative, we know wherever the bigger number goes, the bigger number should be negative, because whenever we add the x times this, x times this, we should have more negative terms. So now we think, if this factors nicely, then we should be able to think of integer multiples of 6 that we can express here and here, such that when you add them together along with these signs after getting multiplied out with FOILing, we would get just a negative x left. And if we think about that, 2 times 3 is 6, they're 1 apart, so specifically since we want a negative x, if we put the 3 here and the 2 here, we can always check our work. This times this is x squared. This times this is negative 3x. This times this is a positive 2x. This times this is a negative 6. That would simplify to x squared. Negative 3x plus 2x is negative x minus 6. and we factored this correctly. Now, since we factored this correctly, this will help us determine where do we need to avoid, because our fraction has issues whenever this equals 0. Well, where does this equal 0? It's the idea of this times this equaling 0 can only happen if they separately equal 0. So we went from looking at a quadratic to now just knowing, well, when does x plus 2 equal 0? At -2. When does x minus 3 equal 0? At +3. So we know we've got issues when x equals -2 and again when x equals +3, because if you substitute either of these values into the quadratic, you would get 0, which means the denominator would be 0 at that point. Now we found the issues, but we do need to write this in interval notation. And specifically this problem only asked about the domains, so let's just list out the domain in interval notation. And if it helps you, whenever you've got multiple things that we need to avoid, we don't want x to be -2 and we don't want x to be 3 because we don't want these to be equal to 0. So it might help to think of this in terms of a number line. -2 comes before +3. Notice this splits our domain, our x values, into 1, 2, 3 sections all about our 2 points of interest. So the way I like to think about this is I would just pick an x value that is in each interval. So for instance, before -2 we could say like -4. Between -2 and 3 we could say 0. After 3 we could maybe say 4. Of course there's many particular points you could pick. Just pick easy ones to work with, and then you'd ask yourself, at -4 is there any problem? No, because the only thing we need to avoid is the denominator of this function equaling 0 because it's a rational function. The only places this denominator equals 0 is at -2 and 3, so we're totally fine here. Then you get to the point of interest itself. Can we equal -2? No, we cannot, because if we equal -2, then this term becomes 0, which multiplies by this term, which takes the whole expression to 0. Notice we can be anything between -2 and 3, because those won't make our denominator equal to 0. We can't be 3 because that would make this term equal to 0, which would send the whole product to 0, which would make our denominator have a 0. But we could be anything after 3 because all we've got to avoid is these 2 points, not -2 and not 3. Because of that, we know our domain for this function is going to be all values before -2, so we'd express that as -infinity up to -2. Now since we're not including -2, we do the open parenthesis, union, and then we pick right back up after -2, -2 to 3. We're not including 3, so we do the open parenthesis, union, 3 to infinity. And that would be our answer for this one. Now for the next 2 examples, we're under the same instructions. Find the domain, both for h of x and f of x. Let's focus on h of x first. Now if we look at the function h of x, it's quite a bit more complicated than our previous example, but with time and practice we're going to be able to recognize certain structures and know where those structures have issues. For instance, do we notice that regardless of the other pieces of this, it is just a fraction? One thing divided by another thing? Well, where do we know that fractions have problems? The fractions, we know for their domain, the denominators can't be 0. And then we look specifically at this equation. What would make this denominator equal to 0? Well, remember, the square root of something can only be 0 if the inside of the square root is 0. So we need to make sure that 7 minus 3x is not equal to 0, because if it ever is equal to 0, square root of 0 is 0. That means we have a 0 in the denominator. So once we rule out where this is, we'll have taken care of the idea that we've got a fraction, that we've got to watch out where the denominator is 0. And now more specifically, let's look at the top of the fraction. and the bottom of the fraction and think, where do they have issues separately, and avoid those as well. Now, one thing to keep in mind is whenever you've got a cube root, by itself, that's fine anywhere. Now, if it's in a more complicated expression like this, you've got to avoid the other issues, but a cube root is fine anywhere, generally. Negative infinity, infinity, and notice what's inside the cube root is just x plus 11. That never has issues. That's just a straight line. But when we're looking at just the square root, which when there's not a number written in this crux here, it's implied to be a square root, this has issues when the inside of the square root is negative. Because if you try to look at the square root of a negative number, you're actually not in the real numbers, you're in the complex numbers. So specifically, where is this square root negative? Whenever the inside is negative, so we need to avoid 7 minus 3x to be negative would be less than 0. So we already could not have 7 minus 3x equal to 0, because that would send the denominator to 0, which is an issue. You can't have 0 in the bottom of a fraction. And then additionally, since the bottom of the fraction, we saw as we looked at its form, it's a square root. Well, square roots can't have negatives on the inside, so that means the inside of the square root we need to avoid when 7 minus 3x is less than 0. Said in the positive sense, or in a different sense, 7 minus 3x needs to be greater than 0. That's okay, right? We either need to avoid when it's negative or be okay when it's positive. You could solve it through any of those both of those routes. I'm going to say let's just worry about avoiding for now, but see that you could phrase it same meaning, different way. Avoid when it's negative, or you're okay when it's positive. So with all of these domain problems, I recommend you do something similar to this, where you just take a bit of time to look at how the function is structured. And then you think about, okay, what is the problem that could come from each piece of the function? We've kind of outlined our steps. We need to figure out this, we need to figure out this, and then we need to combine to a single interval notation, and we'll be done with the problem. So let's start working to find where are these problem areas specifically. So we've basically got two things to consider. The first one is we don't want the inside of the denominator to be equal to 0. So if we solve this for x, we might subtract 7 from both sides. And we get that negative 3x cannot be equal to negative 7. Divide both sides by negative 3. And we would get that x cannot be negative 7 divided by negative 3 is positive 7/3. So we need to avoid when x is exactly equal to 7/3, because that would make the denominator equal to 0, which is an issue. Next, we need to make sure that we avoid when 7 minus 3x is less than 0. Solving this, we could subtract 7 from both sides. We need to avoid when we've got negative 3x is less than negative 7. Now we're going to need to solve for x, so we're going to need to undo this multiplication. So we're going to divide both sides by negative 3. But here's a warning: whenever you're dividing by negatives in an inequality, you have to switch the sign, switch the direction, of the inequality. So just remember that since we're dividing by a negative, the inequality sign, instead of being in this direction, gets switched to the opposite direction. And we get x, we need to avoid when x is greater than positive 7/3. So we're avoiding when x is greater than 7/3. If you solve this in the positive, you would get you're okay when x is less than 7/3. These have the same meaning, right? It's just one is saying avoid this, one is saying it's okay when it's this. It's just based on your preference how you're going to solve it. So I need to avoid when x is greater than 7/3, and I need to avoid when x is equal to 7/3. So let's see this on a number line, and then we'll write our final answer in interval notation for this problem. Okay, so to write this in interval notation, we first would be benefited to just visualize this interval. So the key points, do you see every description hinges around 7/3? There's no other point that seems to be of interest to us in this problem. So I'm just going to label 7/3 on the graph. And notice that kind of splits me into 3 sections: before 7/3, at 7/3, after 7/3. We just have to determine which of those is okay for our function. So we know we can't be equal to 7/3 because it just said don't equal 7/3. And then we need to avoid when it's greater than 7/3. So it's not okay when it's greater than 7/3. That means the only thing left to us is it's okay when it's less than 7/3. So specifically, we're okay from x is negative infinity everywhere before 7/3 all the way up to 7/3. And then think about for a second, what kind of parenthesis would you use? A closed parenthesis or an open parenthesis based on the fact that we can't equal 7/3? And open parenthesis, because open means you can get as close as you want, but don't actually equal 7/3. So the domain for this problem is this. Now the instruction for this problem is the same as before. Find the domain of f of x. Before you start working, I'd recommend that you take a minute to look at how this function is structured. What's the overall structure? What are the component pieces? And when do those things have issues in terms of being a function? Similar to things that we've discussed in the previous 2 examples. And to do this, I recommend that you would take a moment and pause the video. Okay. Throughout our lecture videos, I'm going to occasionally give these pause instructions. I highly recommend you actually pause the video and then work out the problem as described to the best of your abilities. When you're ready and after you've had time to work on it, then you would unpause the video and you'll see the solution worked out before you step by step. And the benefit of this is you've already attempted on your own. So you can check the problem versus the solution you see in the video. And if it's correct, that's great. You get feedback that you are confident in this section, you're understanding these examples. If it's not correct, you also get feedback so you can see if you can correct it. And if you're unsure how to correct it, you can always reach out in office hours, Canvas inboxes, or PSC email. So if you can, why don't you pause the video now and unpause when you're ready to discuss the structure issues from this function and what we need to be cautious about when looking at its domain overall. Now the first thing I look at when I see this function is I very quickly see it involves a fraction. Not even interested in what the fraction's made up with yet. I just know that fractions immediately tell me that the bottom of the fraction can't be 0. And specifically, what is the bottom of the fraction? Square root of x squared minus 25. Can't be 0 because it's in the bottom of a fraction. But more specifically, you know you can't square root something and get 0 unless the inside is 0 itself. So this lends us to the more simplified equation. X squared minus 25 cannot be 0. And I would think of it in terms of that because it is the simpler but equivalent equation to work with. So eventually we will have to solve this, but let's keep looking at the structure of the function to find the other places of issue. Now once I've dealt with the idea of the structure of the fraction, now I'm looking at the individual pieces that make up the fraction and see if they introduce additional issues. Looking at the top, I see that I've got the square root, and again, what's inside the square root can't be negative. So specifically, I need to make the x, what's inside the square root, positive, right? Greater than or equal to 0. And there's a square root in the bottom as well. So what's inside the bottom of the square root also needs to be greater than or equal to 0. Now, it's okay to have 0 inside a square root, but do you see that it also can't be 0 because it's in the bottom of the fraction? So even though the square root is okay with 0, the location of the square root is not okay with 0. So we'd probably improve this to say x squared needs to be greater than, x squared minus 25 needs to be greater than 0 strictly. So if we can translate these three things and then combine them to when they are all true at the same time, we're going to get our interval, and we can write our answer in interval notation. Now, as we're thinking of factoring this binomial, it might be helpful to see that x squared minus 25 is the difference of perfect squares x minus 5, x plus 5. And we want to know when is that. We don't want that to be equal to 0. And if you want to practice the factoring, you might Google difference of perfect squares. That's what we used here. It's a really useful factoring technique, so difference of perfect squares. There's some great Khan Academy videos you could find if you look this up on YouTube. But that's how we quickly factored x squared minus 25 is x minus 5, x plus 5. That can't equal 0. Well, remember, something equals 0 when they're multiplied only if separate pieces equal to 0. So we've got x minus 5 can't equal 0. X plus 5 can't equal 0. This only happens when x equals 5. We don't want that to happen. And this only happens when x equals negative 5. We don't want that to happen. So we've got two ideas. X can't be 5. X can't be negative 5. Maybe we're going to highlight that for later. And specifically, we were already found this can't be simplified anymore. X has to be greater than or equal to 0. And for the last statement, we've got to check whenever an inequality is related to a quadratic, anything higher than a linear equation, then you're probably going to have to solve it thinking through this method, because if it's linear, we can use algebra to solve. But solving when a quadratic is positive takes a bit more nuance and effort. So let's talk about how to solve this inequality here. So whenever you're trying to solve an inequality involving a quadratic, I would recommend you start with your number line, and you first think about when does the expression exactly equal 0. So notice I'm taking the left side, and I'm curious about when does it equal 0. Well, we already found that previously just trying to find other parts of the problem, so normally we'd have to solve this anew, but we already know this. We know that this equals 0 when x is a positive 5 or when x is a negative 5. So again, we are trying to solve this inequality. The first step is to say when is the left side just strictly equal to 0. Then step 2 is to graph on the number line. So graph what was found in part A, or part 1, on number line. So specifically, I'm going to graph the negative 5, which comes numerically before the positive 5 on the number line. And then work on visualizing when you plot the negative 5 and the 5, it took a single number line and splits it into everything before the negative 5, equal to the negative 5, between negative 5 and 5, equal to 5, and then after 5. So you see we've kind of got 1, 2, 3, 4, 5 sections to our entire x-axis. Step 3 is to pick test points, and by test points, I think after you've identified the intervals that it's split it into, notice the first one are things smaller than negative 5. Just pick any number that is smaller than negative 5. Since you can pick any number, pick an easy one, like maybe negative 6. Pick any number between negative 5 and 5. Since we can pick an easy one, why not pick 0? Notice I'm using a different color. I'd recommend that you might use a different color or pen or pencil, or a smaller font if you don't have another pen or pencil that you could use in its place. Everything bigger than 5 is the next interval, but since we can pick, let's just pick 6 because that's very close. It makes our job easier. Now with these test points, you are going to evaluate the test points that you found into the original inequality. In our case, that's this. And you're either going to get a true or a false statement. If it's a true, then you just put a check over that interval that involves that test point. If you get a false statement, then we put an X over that interval that involves that test point. Let's start with our test point negative 6. So I'm going to input this negative 6 into the inequality squared minus 25 that's supposed to be greater than 0. Let's see if that's accurate. Negative 6 squared is a positive 36. If you're typing this into your calculator, remember the negative 6 needs to be in parentheses that you're squaring, because you're squaring all of negative 6. Otherwise, you're going to get a sign error and get negative 36, which is incorrect. 36 minus 25, that's supposed to be greater than 0. Well, when we simplify this, we get 9 is greater than 0. That's a true statement. So since that's a true statement and we plugged in negative 6, then we give a check mark on the interval involving negative 6. That means it's okay to be any value between negative infinity and negative 5, not including it. Next, let's test the next test point at 0. So in the same inequality, you plug in the next test point and see if you get a true or false statement. 0 squared minus 25 is supposed to be positive. Let's see if that's true. 0 squared is 0, minus 25, is that positive? We're kind of checking. Negative 25 is greater than 0. That's a false statement. Negative 25 is smaller than 0, which means we put an X. So it means we can't be anything between negative 5 and 5, because that makes the inequality false. Check our last test point, and at this point I recommend you would pause the video. Check the last test point at 6 as we did with the previous two. Put a check or X based on if you get a true or false statement. Unpause when you're ready to check your work. Plugging in 6 to the inequality here, 6 squared minus 25 is greater than 0. Simplifies to the equation 9 is greater than 0, which is true. So we put a check over here. Now we're not yet done. We need to know, is it okay to be equal to negative 5 or positive 5? Well, remember from a different exercise, we said you couldn't be equal, right? Because that would make the denominator equal to 0, which is a problem for fractions. So we can't equal exactly negative 5, and we can't equal exactly positive 5. Now we're pretty much done with this problem. The way you can verify you don't need to think about anything else is look at all of our constraints. Do you see they involve 0? It said it had to be positive. Now really quick, we have taken care of in this interval here. Let me back up for a second. This interval that we tested only shows these two rules. But did you see that from the square root at the top, we had the even stronger rule that the x has to be positive? And the issue is the denominator square root has no problem when x is negative 6. But imagine if we tried to evaluate our function at negative 6, we would get the square root of negative 6 divided by the square root of negative 6 squared minus 25. Well, the denominator is going to simplify to the square root of 9, which is just 3. But the top, if you try to type in the square root of negative 6 into your calculator, you're going to get an error because this is not a real number. So, especially as we're looking at the domains of more complicated functions, you've got to think of all the constraints at once, and you've got to make sure they all coordinate together. So I'm going to erase these steps here just so we can rewrite underneath, but maybe you can write off to the side. I'm just running out of space. And we're going to talk about how we would combine all of this to a single answer. So as you're working through this, realize, what do your intervals account for? The interval that I just drew, circled in yellow, only accounts for 2 of the 3 constraints. So we need to have another interval telling us that x needs to be greater than or equal to 0. The key point of interest is 0. It said you could be equal to 0, but you could not be smaller than 0, but you could be greater than 0. And now we're going to finish this problem whenever we coordinate these 2 intervals into another one. And there's other ways that you can do this problem. You could also just think through this mentally, coordinating all the intervals. The inequalities. This is just one way to solve the problem. So notice our key points that we're hinging about were negative 5, positive 5, and 0. Everything else were just test points that we picked, so I'm going to put those on our axis. Negative 5 in numerical order, 0, and then positive 5. And it can only be true for the entire function f of x domain if it's true for both of our constraint number lines. So first of all, do you see this is the stronger one? X had to be positive or equal to 0. So that automatically kicks out the first interval, even though it was okay for the top number line, it was not okay for the bottom one. It's got to agree in both number lines to be in the final number line. Now notice in the top it was not okay to equal 0, but in the bottom it was okay to equal 0. But that's not enough. They both have to agree, so at 0 we also can't equal 0. Now at 5, notice at the top you couldn't equal 5. At the bottom, 5 is down here, and it was definitely okay, but since it's not okay at the top, we can't equal 5 itself. And now we just have to determine the remaining intervals. So we said we can't equal these points themselves. And specifically, since x has to be greater than 0, all of this is out, because that's when it's smaller than 0. Now, between 0 and positive 5 in the first interval, do you see that it was an x, right? We couldn't have any values in between negative 5 and 5 for this inequality. So, even though it was okay to be between 0 and positive 5 here, that's from the check mark, it wasn't okay here, so it's not okay here. But it was okay to be greater than 5, and it was okay to be greater than 5 here. Okay, kind of that part of the interval. So it's okay to be greater than positive 5 here. So we kind of coordinated both things. We had to make sure they're both true at the same time, which means we restricted more than either of them had in this case. So our overall answer is the domain of f of x. Okay, why don't you pause the video? Based on this number line, write it out in interval notation, unpause to check your work. Is we can't equal 5, but we can approach it, and we can be anything after 5, right, by that check mark. So we can go from 5 to positive infinity, and that would be our answer for this example. Now, this next example has an additional difficulty to it, and one this difficult is not on a quiz or exam. Now, any of the other ones are definitely fine, but one where you've got a square root, specifically, what do I mean by this difficult? You've got a square root where the inside of the square root is a fraction. That adds another layer of complication in determining the domain. So specifically, one that is a fraction inside a square root is not going to be on a quiz or exam. But if you're interested in the solution, just for your own knowledge, later this week, I will post a solution, a PDF of the solution to our Canvas page. If you want to look over it, but that is completely optional. So just to clarify, there will be domain problems on future quizzes and exams. The only thing that I'm excluding for future quizzes and exams is specifically domain problems that involve a fraction inside a square root. Now, if this is confusing to you, please reach out to me via email or a Canvas message and let me know, and I'll be happy to clarify for it. And if you're interested in studying just for your own knowledge, you can look at the PDF that will be posted later this week to our Canvas page. Now, in part 2 of this video, we're going to start talking about piecewise functions. So continue on to part 2 of this video now.